It's my honor to introduce to you Edward Lee, but all of you, I know you know Edward Lee, but just to do it properly, I'm going to say a few words. Edward has been working on embedded software systems for 40 years, and he has been at Yale, MIT, and Bell Labs, and then finally he landed at Berkeley, and he's now a professor of graduate school in EECS at Berkeley. His research is focused on cyber-physical systems. He's the author of leading textbooks on embedded systems and digital communication, and has recently been writing books on philosophical and social implications of technology. So we had him here before COVID talking about one of his books, and it was great. And now he's here for one of our project meetings, and he gave a very nice half-an-hour talk yesterday at the meeting, and we are going to put that on YouTube because he convinced everyone, including our industrial partners, that they should use formal methods and model checking, much better than what I did. So after the meeting, it was great. So thank you, Edward.
Thank you, Marjan. It's a real pleasure to be here, and thank you all for being here. And don't hesitate to interrupt me with questions and comments. I'm going to be talking about a topic that is kind of near and dear to my heart, and it's a little bit technical, and so I ask your forbearance. The references are in the form of archive papers, and I love the opportunity here to actually talk about these results, since they don't seem to want to hear about them at the mainstream conferences. So I guess you will be the judge about the significance of this work, but to me, it's actually very foundational. And to give you kind of a really high-level view, I see this as almost like a Heisenberg uncertainty principle about distributed computing. It has to do with the core idea is that in a distributed system, when you need certainty, which in many of the systems that we're interested in, you do because they're safety critical systems, that when you need certainty, you inevitably pay a price in time delays. So there's a trade-off between time delay and certainty. And that's really what this talk is about, is that fundamental trade-off. Now, we're not the first to observe that there is this trade-off. In fact, there's this very well-known theorem. It's actually a statement that is unbelievably obvious. So, you know, it's almost insulting to mathematics to call it a theorem. But it comes from the database community, and it was first articulated in this form by my colleague at Berkeley, Eric Brewer, who gave a talk at a keynote talk at PODC, where he introduced this idea that he called the CAP Theorem. And CAP is an acronym that stands for three different things: consistency, availability, and tolerance to network partitioning. Now, this is, he was coming at this from the database community. And in databases, the idea of consistency is that if you have a record in the database, and the database is a big globally distributed database, then you're going to have copies of that record scattered in different data centers throughout the world. Okay? And consistency is simply the idea that all the copies agree on the value of the record. Okay, so for example, if it's a record recording airline seat assignments, that, you know, if you check you access a Dallas data center to ask whether the seat is available, in some sense you will get the same answer as if your query went to a database in Singapore. Okay, so there has to be that notion of consistency, is that the record, the value of the record is well defined across the database, even though the data is replicated. Availability is the ability that the database has to respond to your query. So when you ask, is this airline seat available, can the database give you an answer, right? If it takes a long time for the database to give you an answer, the database is less available than if it can give you an answer right away. Okay? If it can't give you an answer at all, it's completely unavailable. Right? And network partitioning is simply loss of network connectivity. And so the statement here is really obvious. If you lose network connectivity, okay, then Singapore and Dallas have two choices. They can either give you an answer about whether the database is available, in which case they're available, the database is available, but there's no assurance of consistency. Or they can not give you an answer because they have no assurance of consistency, and then they're unavailable, right? So what Eric was basically saying is that there's this fundamental trade-off between consistency and availability, and when the network breaks, you have to give up one or the other of consistency or availability. Okay, it's obvious, right? No problem. So how does this translate to more general systems, not just databases? Well, the idea here is that if you have any two software components that are interacting over the network and they have some shared variable, so it might be, some state variable, they might represent their view of the world, okay? Then consistency is simply agreement on the value of that shared variable. And availability is the ability to respond to reads of that variable, right? In my group, we're particularly interested in cyber-physical systems, and so we're interested in the situation where these shared variables represent your view of the state of the world. Okay, they might be sensor readings or something like that. So the value of X is the value of some sensor reading, and it's telling you something about the physical plant around you. And so consistency in this case becomes agreement about the state of the world, right? So let me give you two examples that show that. I think we agree, we're all on the same page that Eric Brewer was right. If the network breaks, you have to give up one of consistency and availability, right? So the first statement I'd like to make is that which of those you should give up is very application dependent. There's no way that the software system can decide for you whether to give up availability or consistency. You're going to have to choose when you design the system which you're going to give up, okay? So to give two very concrete cyber-physical system examples where the answer is opposite for the two, okay? In this particular example, we want to give up consistency if the network breaks, okay? So let me give you a very specific description of this. So this was a demo. The image here is a demo of a ADAS system, Advanced Driver Assist System, which many cars today are equipped with. They have forward-looking cameras, and they do analysis of the scene, and if they detect pedestrians, they apply the brakes, okay? And this particular demo has a cardboard pedestrian standing in front of this car and a driver who's trying to speed towards the pedestrian, and sure enough, the car stops, of course, right? So how is this implemented? Well, you have a camera that takes a snapshot of the world at some time t, and then you have this braking assistance system, and many people these days are very interested in doing the computation for this braking assistant in the cloud. Okay, scares the hell out of me, but nonetheless, they're talking about doing that. So maybe you take this snapshot, you ship it off to the cloud. You wait for a response from the neural networks that are implemented out there about whether it's a pedestrian, and you use that result to drive the braking signal. But in addition, you have a brake pedal, and that's a local thing. And when a driver presses the brake pedal at some, say, time t plus epsilon, so a time a little bit later than the snapshot was taken, okay, what should you do? So now you have this braking system. You're designing the software for this. And the fact is that the view from the camera is a slightly earlier view of the physical world than the view from the brake pedal. slightly later at t plus epsilon. If you insist on consistency, this brake component should process the camera information before it processes the brake pedal information. But then that means that this brake pedal component, the software component, should wait for a response from the cloud before it applies the brakes when someone pushes the pedal. Is that the right thing to do? No way, right? I mean, think of it in Eric Brewer's term, right? If the network breaks altogether, how long is it going to take to get the response from the cloud? Well, it's an indefinite amount of time. So this brake component, if you emphasize consistency, the brake component's just going to sit there waiting until the network gets repaired. And then when the network gets repaired, it'll say, oh, there was a pedestrian there, and apply the brakes, having ignored the entire time this signal. Right? So very clearly in this case, you want to emphasize availability, and you want to do this at the expense of consistency. Right? Now, I'd like to emphasize that it's so obvious in this case, but that's only because we know the semantics of the system. Right? If you're software, you have no idea that you're applying a brake to preserve a pedestrian's life, right? So there's no way the software can make this choice for you. This is very specific to the design. So let me give you another scenario where the answer is exactly the opposite, where you want to emphasize consistency over availability. It's also a automotive control problem. You have a four-way intersection, and you have a roadside unit that is coordinating self-driving cars that are sharing this intersection. Okay, so as each vehicle approaches the intersection, it contacts the roadside unit, tries to get permission to enter the intersection, and will cross the intersection when it gets granted access to the intersection. Okay, so the question is, what should the car do when it loses network connectivity? Right? Should it proceed on the basis of inconsistent information that it has about the world? Probably not. You'd rather have the cars stop at the intersection, sacrifice availability, rather than have the cars proceed on the basis of inconsistent information. So this is an example where you really want to emphasize consistency, and if you lose network connectivity, you'd rather have the vehicles just stop. So the key observation here is that the choice that you have to make between consistency and availability can't be made for you by the software infrastructure. It's application dependent. Okay. So the first problem that I'd like to address, and the one that I think is the primary reason why this paper keeps getting rejected, is that this notion of consistency seems perfectly intuitive, but it's actually extremely subtle. What does it mean for two separated components to actually agree on the value of the state of the system? Okay. What is agreement, right? Let's look at a very simple and very concrete example that I can use to show you that actually agreement on the state of a distributed system is fundamentally impossible. Okay, it actually cannot be accomplished. So here's a very simple scenario. You've got two physically separated state machines, each of which makes a state transition. So the one on the left transitions from state A to state B. The one on the right transitions from C to D. The state of the system starts out in A and C. Okay? So the question now is, each of these makes a state transition, and you eventually end up in B and D, but what about the intermediate states? Well, I mean, if the left one makes the transition first, then you will take this path. If they make the transition simultaneously, you will take this path. If the right one transitions first, you will take this path. But what does it mean for the left one to transition first? Okay. If you've studied relativity, you know that if these transitions occur sufficiently close together, then there is no ground truth to which one transitions first. In different frames of reference, the left one transitions first. In another frame of reference, the right one transitions first. And both of those are truths, not just observations. They're actually truths. Okay. So there's kind of a fundamental problem in that somehow, maybe we could think that the system was in this state, but actually it could have been in this state in a different frame of reference. So actually the state of the system in this intermediate period is actually not fundamentally definable. So there's a bit of a fundamental problem, but there's also a very practical problem, right? The practical problem is that in any distributed system, you actually don't have a shared notion of time. The best you have is some local physical clock that's attempting to measure time, but all clocks are imperfect. No two clocks are perfectly synchronized. So a statement like, well, let's just say that any observer agrees at a particular time on what the state of the system is, that doesn't work either, because the different parts of the system have disagreements about what current time is. Okay, and from a practical perspective, it's quite difficult to fix that. And you might think it's a little bit odd to, be invoking relativity in sort of macro scale operations, but I'd like to point out that in a way these are not really so macro scale, right? The systems that we design routinely do things on nanosecond scales. The order in which events happen can have a big effect on the behavior of the system, and this is a nanosecond at the speed of light, okay? And these systems often span the globe. So, so these problems are both practical and actually fundamental. Yes, question?
You have some practical problem, but for the theoretical problem, if you reduce the observer kind of notion, would that be able to say that this is the ground truth of the system, because observer would observe of the system?
Yeah, in the theory of relativity, if you pick a fixed frame of reference, okay, and take that as your ground truth, you can do that.
Yeah.
Okay. But how do you pick that fixed frame of reference, right? And if you've, well, we could go down a whole different rabbit hole on that. But so let's just focus on the practical problem, right? The practical problem is you can't agree on what the current time is, and therefore there's always going to be some ambiguity in any decision you make about what the state of the system is. And the fact is that the systems we are designing these days are almost all digital, which means that they do stuff in discontinuous ways. Okay, they make decisions that are discrete decisions, right? So, for example, you might have a system that if this state ever occurs, deploys the sprinklers in the building, all right? A drastic action, and you don't want to take that drastic action on the basis of ambiguity. Okay, so the problem of what do we mean by agreement is really a fundamental one. So let's take a really practical example. Let's look at a global database that's handling a banking system. So Joe's bank balance starts at $50, and you have a deposit that occurs in London at 10 a.m. GMT that adds $100 to it, right? And a withdrawal in Singapore that at 10 a.m. GMT plus 10 milliseconds withdraws $110. So now my question is, was Joe's bank balance in overdraft? Right? Should we send him a bill, a discrete action, for an overdraft fee? The bank has to make a decision about this. The fact is that if at the speed of light, Singapore and London are actually 33 milliseconds apart, which means they're outside of each other's light cone, okay, which means that the actual true order of these two events will depend on your frame of reference, the true order, okay? So should you send an overdraft fee or not? Well, in one frame of reference, yes. In another, no. But you have to make a decision. So how should you make a decision? By the way, just as an aside, I asked DALL-E, which is this image synthesizer from OpenAI, to generate a picture for me of a globe showing both London and Singapore. This is what it came up with, which is it invented a new place in the world whose name is some combination of Singapore and London. I thought that was a really bizarre reaction, but anyway, so that's why I included this image. Okay, so how should the bank? Yes, question.
For banks, don't they have strong consistency?
Yes, but I'm going to show you what we mean by strong consistency, and it's not based on ground truth about the order of events. And that's the essential point that is so subtle that I think that the reviewers never got when we submitted this paper. It's not about ground truth. It's about semantics. Okay, so here's how the bank should deal with this. When the deposit occurs in London, it should timestamp it with a local clock, just some physical clock that's measuring time. When the withdrawal occurs in Singapore, it should timestamp it with a local clock. It can't timestamp it with London's clock. Okay, it's got to use a local clock. And now the bank should simply define the order of these events to be based on the numerical order of these two timestamps. That's a semantic property now, not a ground truth anymore. Okay, now these two events have an order, and it's a numerical order. And now your challenge is simply to design the global system so that every part of the system always sees events in timestamp order. Okay, and we know how to design such systems. By the way, it's not easy to design a system to do that, but we know how to do that. Okay, so this is the semantics of the database system, is that transactions occur in timestamp order, and the timestamp is drawn from a local clock. Now, for this to be useful, of course, you probably want those clocks to be at least somewhat synchronized, right? They shouldn't be many hours apart, right? Otherwise, customers are going to complain. But the semantics of the database doesn't care, right? The semantics is the same whether the clocks are synchronized or not. Events are, by definition, occurring in timestamp order. Okay, so the key idea here is this separates a notion of logical time from a notion of physical time. The timestamp, as soon as it's assigned to an event, becomes logical time. It's no longer, you don't even need to think about it as being a measure of physical time anymore. Its meaning in the system is that it defines the order of that event with respect to other events that are occurring in the system. That's the key idea. So in this case, an event in the model occurs instantaneously at a logical time, where that logical time is simply drawn from a totally ordered set. And you ensure that all observers in the system see all events that they see in logical time order. Right? Any two events that have the same logical time are logically simultaneous. In physics, the notion of simultaneity is nonsense, right? But here, it's just numerical equivalence. It's easy, right? The bank is going to have to decide how to handle logically simultaneous events. If the deposit and withdrawal got the same timestamp, should they send a bill or not? Well, that's a business decision. Okay, you encode that in the logic of the software.
But the clocks are physical. How do you determine which happened before?
The point is you don't. Right.
But once you get there, you don't need to do it anymore. But
right.
I mean, this time, depending how synchronized clocks are, what is the difference between one could happen before the other, and the other way around if the clocks are.
That's right. And the point is that we cease to care about the question of which one actually occurred first. We just define the system's behavior on the basis of the timestamps that are assigned.
That's the subtle point?
That's the subtle point, yes. Yeah, it's the way that I think of it as it's a distinction between a logical notion of time and a physical notion of time. Another way to think about it is there's a difference between scientific models and engineering models. Okay, a scientific model is one that's required to behave like some physical system. Right? That's why we build scientific models. But engineering models actually do the reverse. If you have an engineering model, you try to make a physical system that behaves like the model. All right? Complete mirror image. Logical time is an engineering model. Physical time is a scientific model. And we stop treating time as a scientific model in this system and start treating it as an engineering problem. So our problem becomes simply, how do you usefully assign timestamps to events? And then how do you ensure that every observer sees events in timestamp order? Okay. So if we look at it from the perspective of this software system, if we have an update to the variable x, we assign that update a timestamp based on a local clock. We would like the other software component to be notified of that event. Okay, so we send a message to it containing the timestamp. All right, and the other software component then does an update as well at a logical time. Now, I'm going to show you in a little bit that it's often useful to allow the update here to actually occur at a later logical time, because I now will be inconsistent for a brief period of time, and in exchange for that, I can improve availability. Okay, so this is the key idea, that if I allow a little bit of inconsistency, I can improve availability, and I can play with this trade-off between availability and inconsistency and do it explicitly. So that's going to be the key. So let's dive into the technicalities here, all right? So how do we define, well, it's actually more useful to define inconsistency than consistency, okay? So inconsistency from an update occurs at node J, and node I is informed of that update, and the update at J has this logical time, and the update at I has this logical time. If the two are equal, and always equal, okay, then we have perfect consistency. The inconsistency is always 0. But we're going to allow a little bit of inconsistency sometimes so that we can get improved availability, right? So inconsistency from node J to I is the maximum over, the theorem that I'm going to give you, which we call the CAP Theorem, is a theorem about an entire program and an entire execution of a program. Okay, so it looks at maximum inconsistency, maximum unavailability, all right? So the maximum over all updates on J that are sent to I of the difference between the two logical times, the logical time at which the original update occurs and the logical time at which the replica's update occurs. Okay, when those two logical times are equal, we have perfect consistency. Okay, so you can see that the consistency will always be greater than, well, we make this a constraint actually. We don't allow a negative time delay in an update, okay? And that turns out to be convenient, but it's a constraint. So we call this perfect consistency, strong consistency. Okay, so strong consistency now becomes all nodes agree on the value of the variable at a logical time t. And now this is well defined. Unlike the sort of vague notion of consistency that, well, they agree at some physical time. Well, we don't know, we don't have access to that physical time. Now we have an unambiguous, checkable definition of consistency. Okay. So how does this apply to the car braking example? Well, the camera timestamps the frame that it takes. Logically, the braking assistant is logically instantaneous because the information it's going to give us about the world is about the state of the world at the time that this timestamp was taken. Okay, so we ignore the physical time delay of communicating with the cloud. That's not relevant to the consistency story. So we get an event from the cloud that tells us whether there's a pedestrian, and that still has logical time t1. And now, when the brake pedal is pushed, that also gets assigned a timestamp, maybe using the same clock or maybe using a different clock. You know, it doesn't matter from this perspective. That event gets a timestamp as well. And if we require strong consistency, then we require this component to see these events in timestamp order. And we now know that for this application, that's the wrong thing to do. Okay. Strong consistency here reduces availability. So we can quantify availability too. And it turns out that availability it's more convenient to quantify unavailability than availability. Okay. And the unavailability is now a comparison between logical time and physical time. So this is the timestamp of an event. Okay, so it's the logical time of an update of a shared variable at node I. Okay, so you're at node I, variable changes at a certain timestamp. Capital T sub I is the physical time at which someone can access that variable, when the software will let you read the value. Okay, so the update has a logical time, and when you go to read that value, that read is going to be permitted at a certain physical time. The difference between that physical time and that logical time is the unavailability. If that difference is big, then your system is less available than if that difference is small. Okay, so we again impose a constraint that the unavailability is greater than or equal to 0. So perfect availability is where you always respond immediately. You can respond immediately whenever anyone tries to read the value of the variable. Okay, there's 2 other quantities that we have to define, and then we have all the structure for this system. One is, I said, if you look at this unavailability, okay, let me back up a second. Whoops. The update to the variable occurs at a logical time. When you try to read that variable, the software will let you read it at a physical time. Why wouldn't it let you read it right away? Well, because the software has to ensure that everyone reading this variable sees all events in timestamp order. That's what the software has to do. So the software may have to delay your read in order to make that guarantee. I won't go into here how you implement that, right? I said it's hard. You want to hire an expert to do that implementation, but I promise you, we know how to do it. Okay, we can make a distributed system where everybody reads events in timestamp order. But a consequence of such a system is that when you go to read a variable, you may have to wait. And we call that amount that you wait the processing offset. And it's similar to an unavailability, except that you can think of it as the delay in actually performing the update. So you get a notification over the network that the variable value is going to change at a certain logical time. But you can't necessarily update it right away, because maybe there's already readers that are working on it or something like that. Okay? And you have to ensure that everybody sees these updates in timestamp order. So you take some physical time to do the update, and we call that the processing offset. One more quantity, which is one that we call the apparent latency. Okay, and that's the difference between the logical time at which the original update occurs at the source of the update, okay, and the physical time at which the update is received at the node that is going to perform the update. Okay, so a change to the balance occurs in Singapore. Gets assigned a logical time. That's this number. A message gets sent to London that this change in the balance is going to occur at this logical time. That message is received by London at this physical time using London's clock. Okay, this is why we call this an apparent latency. It's not a true latency. London's clock, according to London's clock, it receives the message at this time. The message contains a timestamp, which tells it at what time the update occurred according to Singapore's clock. Okay, 2 different clocks. But this is a totally measurable quantity. It's easily, trivially measurable. The actual delay in the communication is actually not measurable. Right? You can measure round-trip delays. You can't measure one-way delays. It's physically impossible to measure one-way delays. But this quantity, apparent latency, is easily measured. Right? You just look at your local clock when you receive the message. You look at the timestamp. The difference between the two is apparent latency. Now, you can think of the apparent latency as consisting of a whole bunch of different things, right? There might have been some delay on the sending node due to the constraint of doing things in timestamp order. That's the processing offset on the sending node. There might have been some execution time involved, software that had to execute to send the message or whatever. There's some network latency, and there's a clock synchronization error. Okay? All of those contribute to this apparent latency, but I'd like to point out that the only one of these 4 quantities that is easy to measure is this one, OJ. The others are all really hard to measure. And in fact, this one here, Lij, is impossible to measure, physically impossible. Okay. Clock synchronization error, if the 2 clocks are actually in Singapore and London, is also impossible to measure. You have to bring them into the same room to be able to measure clock synchronization error. So each of these individual contributions to Lij are unmeasurable, but the total is completely measurable. Okay. So we put all these together and we get what we call the CAP Theorem, which is a quantification of the CAP Theorem. And it's a relation between the unavailability, which is given as the maximum of the processing offset. So the unavailability at node I is either the processing offset at node I or the difference between the apparent latency and the tolerance for inconsistency. Okay, if you allow inconsistency, then you can improve availability. If you just allow a certain amount of inconsistency, that gets subtracted out from your network latencies. Okay. So in words, the unavailability is the larger of the local processing offset to ensure that timestamps are processed in order, or the apparent latency minus the tolerance for inconsistency. So this gives us a numerical trade-off now. Now we can play with these numbers, not just, a sort of broad policy. So it turns out that that equation that I just showed has a very beautiful formulation in an alternative algebra called the max plus algebra. Okay, this is a vector of unavailabilities. This is a matrix that characterizes your network and point-to-point tolerances for inconsistency. So you can have a completely heterogeneous network. You can have, some nodes have very fast connections. Some nodes have very slow connections. That all gets encompassed in this matrix formulation. And then this is a vector of processing offsets. So you get a linear equation that relates these things. Okay, so we call that the CAP Theorem. Now, let me show you how we can use it in practice. And we use it in this, we discovered this theorem actually because we realized that we were building this programming framework for writing programs for distributed real-time systems. And we realized that we could actually trade off consistency and availability. And this actually came up in the context of the ADAS example. So one of my co-authors on this is Christian Menard, who's a PhD student at the Technical University of Dresden. And he built a program in Lingua Franca for the ADAS system, exactly the one that I just showed you. In fact, the diagram that I was showing is rendered by the tools for Lingua Franca. And he sent me an email and said, there's a really bad feature about this program, which is that the brake pedal is not going to get applied until you've got the results from the image analysis. That's what Lingua Franca will do for you. And I thought about it and said, yeah, but that's because you're insisting on perfect consistency. And I suggested to him that he just put a logical delay into the system to tolerate a certain amount of inconsistency, and the problem goes away. And that's when we realized that there was really something fundamental going on. So the way that I'm not going to go into the lingua franca too much, but let me just say the point is that this diagram is actually generated automatically from a textual description of the program that looks something like this. Okay, where you define your components, you define their interconnections, you define the functionality in reaction to events, and so forth. And you get an automatically generated diagram of the structure of your program. So what I suggested to Christian was, if your estimate is that it's going to take about 10 milliseconds or less to do the image analysis and the communication, then just put in a logical delay, which in lingua franca, this is the syntax here. This is, by the way, if you're familiar with the timed Rebecca language, which comes from Marjan's group, okay, this is exactly the after construct in timed Rebecca. And so you can use timed Rebecca to model these programs in very much the same way that we do in lingua franca, okay? This adds a 10 millisecond increment to the timestamp. So what happens is the camera will timestamp the event, the braking assistant will do its computation, the braking system will see this with an incremented timestamp, which means that we're allowing the braking system to have a slightly out-of-date view from the camera compared to the brake pedal. Okay, and then the CAP theorem will tell us, in fact, that precisely if the time delays associated with the braking assistant analysis and the communication are less than 10 milliseconds, then the unavailability of the brake pedal becomes 0. You can respond immediately to a brake pedal command. Okay. This is what it looks like in the max plus formulation. It's a very simple system because there's only 2 components. So the matrix describing the network delays and computation times in terms of apparent latency is just a 2x2 matrix. And you can solve the equations in a very straightforward way for this example. So you can derive the availability numbers that you get for particular latencies. Okay. In lingua franca, you can go a step further and actually specify your requirements on availability as well. So in particular, I could say, for example, that I require that the braking system apply the brake within 3 milliseconds of this event getting timestamped. Okay, this is an availability requirement. It's a bound on the unavailability, right? And we will consider it a fault if that bound gets violated. So we specify the unavailability requirement. We specify the tolerance for inconsistency. We can now use the CAP theorem to derive what we need the network to do. Okay? And in fact, with this 3 millisecond tolerance and this 10 millisecond tolerance for unavailability, we can derive using the CAP theorem that we have 13 milliseconds to send this frame to the cloud, do the analysis, get it back, and deliver the response. That's pretty tight. I wouldn't use cloud computing for that. Okay, you're not going to get 13 milliseconds reliably, not using some Amazon Web Service. Okay, so go back to Denso and say, hey guys, maybe you should do this in the edge, not the cloud. Okay, but the CAP theorem tells you this. But now, okay, so now you derive the network requirements. You've got 13 milliseconds. All right, so now, all right, you put it on the edge. It still takes some time. And sometimes it'll actually obey the 13 millisecond bound, and sometimes it won't. Something might go wrong. A wire breaks, right? You're going to get a violation of your requirements. The CAP theorem tells you now, and in fact the CAP theorem told you this before, you're going to have to do something. You're going to have to either give up consistency more, or you're going to have to give up availability more than you've specified. Okay, so you have a choice. When you get a failure, you either have to further sacrifice availability or further sacrifice consistency. So you have to design this into your system. It turns out that we realized that, another PhD student, Surush Bhateni, who was doing his PhD at the University of Texas at Dallas, we were working with him pretty closely, and I described to him two ways of coordinating a distributed system. And he blew my mind and went and implemented both of them in like a few weeks. They're pretty hard to implement. Okay? This was, I was very surprised that he was able to put this together so quickly. It was an outstanding piece of work. He's, by the way, been hired by Apple now, and is rumored to be working on Apple's automotive technology, but Apple doesn't tell you, and he doesn't tell me, so that's just a rumor. But anyway, he implemented these two techniques, and it turns out that the two techniques had a very interesting property with respect to this theorem. That one of the techniques automatically sacrifices availability if you get network failures, and the other one automatically sacrifices consistency if you get network failures. Okay, that's what they do. So the one that sacrifices availability, it uses a protocol that guarantees that every component sees events in timestamp order, even if your network collapses completely. But in exchange for that, things can grind to a halt, and you don't get responses to queries anymore because you've lost network connectivity. You can't guarantee consistency anymore. The other one does the opposite. Every component continues to run as long as its physical clock continues to run. But every once in a while, if the network fails, you might see events out of timestamp order. Okay? Because a message got sent, it got lost because the network broke. Eventually, it got sent again. You now get it. It's way late. It's out of timestamp order. So you sacrifice consistency instead of availability. It turns out that the technique that's implemented here is actually used by Google in what is probably the world's biggest database, which is Google Spanner. So this is a replicated database that has copies of the database in entirely distinct data centers scattered around the world. And it uses this same technique that will bound inconsistency. So the database will keep responding to queries, even if an entire data center goes down somewhere else. But the cost of that is that occasionally you lose consistency. So you can also go a step further in Lingua Franca and completely sacrifice consistency. You can design your system so that you say, well, I don't care about consistency. I really want to emphasize availability over anything else. Always respond to the break battle right away. So in Lingua Franca, you can specify that using what we call a physical connection here. And essentially, the simple way to think about this is that even though the camera image gets timestamped here, we just throw away the timestamp. We don't use it for anything. And when we send the information over the network, and when it gets received at the far end, it gets assigned a whole new timestamp. Okay, so that just says, I don't care about consistency. Let's just design this system for availability. So that's also a possibility in this language.
Maybe it's kind of like give priority to some signals. Can you say it like that? I don't know. That would be different.
Yeah, priority is different. In Lingua Franca, the way you control priority is by specifying deadlines. Okay, that gives guidance to the scheduler. Things with earlier deadlines get given priority over things with later deadlines. But priority is a pretty weak way to specify real-time properties in our view. The deadlines themselves are much more concrete than a priority. And in Lingua Franca, you not only specify a deadline, but you specify a fault handler, a piece of code to invoke when that deadline is violated. Okay. So I'm not going to go over the details, but the distributed database that I talked about, the banking example, you can implement in Lingua Franca. And this is an image that has 4 replicas of the bank that can be distributed around the world. And this particular design is enforcing strong consistency. So the banking transactions will always be given, will be handled in timestamp order. If the network fails, availability goes out the window. And that's just a particular design choice, but you can make other design choices. So I'm going to skip over the details of how that's implemented. You can just take my word for it, and we can talk about it offline. So in summary, Eric Brewer's CAP theorem says that network partitioning means you have to sacrifice either consistency or availability. It's obvious. The CAL theorem is less obvious because it rigorously defines consistency, which was completely absent in Eric's work, okay? And it quantifies it, okay? And it quantifies unavailability, and it gives you a numerical relationship between them. And it gives you a relationship between those quantities and network latencies, but more interestingly, not the unmeasurable true network latency, but the completely measurable apparent latency. By the way, apparent latency can even be negative. If your clocks are sufficiently unsynchronized, you could receive a timestamped event that looks like it was generated in the future. Okay, that's perfectly fine. The CAL theorem handles that, no difficulty. It's apparent latency. You get a negative apparent latency in that case. So the CAL theorem gives you a numerical relationship between these quantities, and what it tells you basically is that as network latency increases, either inconsistency or unavailability or both must increase, and it tells you by how much they must increase. We have these 2 coordination mechanisms, one of which automatically sacrifices availability, and the other one of which automatically satisfies consistency if you can't meet your predefined specifications for those quantities. And in both cases, there's fault handling mechanisms that are provided in this Lingua Franca language, so you can react to situations where you've lost availability beyond your specified deadlines, or you've lost consistency, meaning you're seeing things out of timestamp order. Okay. So the really shorter summary of my talk is certainty takes time, where by certainty we mean consistency here, and taking time means you pay a price in availability. So these are the references. The first one here is very much aimed at the database community, but they're not interested in hearing this story. This one is aimed at the cyber physical system community, and they don't understand the story yet, which is probably our fault. We just aren't explaining it well enough. But anyway, thank you very much.